Hey guys, Professor, and we're back for another video. Inside this video, we're going to be talking about the intro into IB chemistry. So in this video, we're going to be just covering some of the basic topics inside of IB chemistry, just the very intro, major concepts which will help you build your foundation inside this course. So with that note, we're going to start talking about this. So one of the first things I'm going to be talking about is the two types of heat reactions, so endo and exothermic. So we have endo, let's move over, so we have endothermic and exothermic. And the way I like to remember what each one does is by looking at this. So we have endo and exo. Well, exo just means that you're going to release something. So in this reaction, we're going to be releasing heat. And the main objective is to get heat outside of the reaction. That's what we're trying to produce. And endothermic is that we're going to absorb heat. And that's going to be just a very basic and simplified version of each reaction. There is a bit more into each reaction, but that's just pretty much the basic thing. That either we're going to release heat or we're going to absorb heat, either if it's endothermic or exothermic. We're just going to, if it's exo, we're going to release. If we're endo, it's going to absorb. And moving on from that, I'm going to be talking about yield and absolute atom economy. So if we have atom economy, what we're talking about is not about the Great Depression or how many jobs each atom has. It's actually just talking about the reaction itself. So when we have atom economy, what we're going to have is we're going to have the molecular mass of useful products. So by useful products, I'm going to give it UP, useful products, over the molecular mass of a reactant. So I'm just going to put reactants as a capital R. And we're going to times this by 100%. And when we're talking about molecular mass, we're pretty much just going to be, this is dealing with how good a reaction is by being efficient. If a reaction is not efficient, it's generally going to have a very low and poor atom economy, depending on what the actual useful product is trying to get released from it. So let's say we have it as photosynthesis. Let's do a different reaction. So let's say we have water, for example. Well, we have H2 plus O2 produces H2O. Well, firstly, let's balance these. So we have to get this. We have to get this. And let's just do the actual molecular mass of what this is going to be. So let's say our useful products is water. We want water out of this. So we're first going to find the molecular mass of the reactant. So, well, we have H2, so that's 2, and then 2 times 4, that's going to be 4. And then O2, well, that's just 16 times 2, so that's going to be 32. This is going to be 4, and this is going to be 32. Well, in this, what we're going to have is we're going to have the useful products on top, so we have 36 over 36 over 36 times 100%. And pretty much what this is going to give us is that this reaction has a efficiency of 100%. And when we have a reaction with 100% atom efficiency, that means the reaction itself is very efficient when it's actually doing it. So let's say we have a reaction which is not very efficient. So let's say we have something like photosynthesis, for example. And for photosynthesis, what we want to do is that we want to get glucose as our useful product. So let's just move down and let's do it. So we have 6CO2 plus 6H2O produces C6H12O6 plus 6O2. And what we want is that we want to find our only useful products is glucose, and our waste is going to be oxygen. So what we're going to have is, let's just do this. So we have carbon 12, so we have 6 times 12. Well, 6 times 12 is simply just 72. So we have 72 here. And then 16 times 2 times 6. So you have 16 times 2 times 6. Well, that's just going to be 192. And then we have water, so we have H2, so that's going to be 12. And then 6 times 16, well, 6 times 16 is just 6 times 16 is simply just 96. And we're going to have to do this, so we have 6 times 12, so 6 times 12, well, that's going to be 72, 12, and then 06, so that's going to be actually just 16 times 6 again. That's going to be 96. And then if you add this all together, what you have is that we have 72 plus 192 plus 12 plus 96. That's 372 as the reactants. And for the actual glucose, we're going to have 72 plus 12 plus 96. That's going to be 180. And when we're doing the reaction, we're going to have useful products on top. So you have 180 over 372. And when we have 180 over 372, if we get the percentage out of that, that's going to be more or less around 48.4%. 48.4%. And this is going to have a very poor efficiency then. So the atom economy in this is going to have a very poor efficiency. But if we're talking about something with yield, well, yield is simply just what was expected and what was actually produced. So if we get rid of this, and let's say we wanted 13 grams of glucose. So we have 13 grams of glucose. That was what we wanted, so that's expected. And then let's say we had 7 grams. So let's just say, we kind of got screwed and we kind of got jacked, so our reaction only gave us 7 grams of glucose. And then this is going to be real. And when we're doing yield, what we're going to have is we're going to have actual yield. So this is going to be 7. And we're going to have it over the expected yield, which was 13. So 7 over 13, well, when we do that as a percent, that's going to be more or less around 54%. 54%. So this actual thing is going to have a 54%. Well, our atom economy and our yield is pretty similar, but let's say instead of 7 grams, we got really screwed up. Let's say we only got 1.5 grams of glucose. Well, let's get rid of this. Let's say we have 1.5. Well, when we have 1.5, what our actual thing is going to be, it's going to be more or less around 11.6%. So 11.6%. Well, now our yield is 11.6%. Well, that's not that good. Because atom economy and yield are not linked together. You can have a very high yield. Maybe if you're expecting your actual were exactly the same or very close to the same, but you had a lot of wasteful products. Well, your yield might be high, but your actual atom economy is extremely low. It's because they're not connected. They can have influences on each other. You'll generally have either a high and high or a low and low, or you might have a low and high. But they won't be the same. They don't have a correlation between each other. It's just because they're not related. They have two different parts. They have two different functions. So moving on from that, I'm going to explain another topic which I see a lot of people struggle with. And that's the concept of a mole. Well, it's not the mole that you would see digging a ground or a mole on like your face or something. It's actually a mole in chemistry. And this mole is represented by Avogadro's constant, which is 6.022 times 10 to the 23. And when you have 6.022 times 10 to the 23, we're just going to call this a mole. A mole is a number, and this number is this constant. That's all a mole is, basically. And pretty much people get confused because, well, when they hear a definition, and the definition pretty much says 1 mole of carbon, 12 atoms, and 12 grams of carbon. That's a lot of the definitions of what people see when they hear a mole. Well, that pretty much just means that any atom, so let's just say we have lithium, for example. Well, lithium is going to have the exact amount of atoms as carbon 12, equals to carbon 12. 12 carbon. So, carbon 12 and lithium are going to have the exact same amount of atoms. So, if lithium has 6.022 times 10 to the 23, and this has 6.022 times 10 to the 23, that's all the definition is saying. It's saying that any atom will have the exact same amount of particles present as compared or relative to carbon 12. People get confused when they hear the difference between mass and particles. Particles are just the amount, and that's the number which Avogadro, that's Italian scientist, pretty much formulated about the number of the particles inside that atom. The atom does not mean the mass itself. So, lithium has a different atomic mass or relative atomic mass compared to carbon's relative atomic mass. You cannot have something with equal relative atomic masses if they're two different atoms. That's the entire point of its actual thing. So, if we have something like hydrogen, oxygen, let's say boron, and let's say fluorine. Well, these are all going to have the opposite amount or different amount of masses, but they're all going to have the same amount of particles, which is 1 mole. Remember, a mole is just 6.022 times 10 to the 23. So, confirming that, so that we know that now moles are just a number which represent the amount of particles inside the atom, let's give the difference between what I see a lot of people struggling with. So, let's get rid of all of this, and let's talk about the different types of atomic masses. So, atomic mass, relative atomic mass, and molar mass, and molecular mass, and formula mass, and they're all going to have the same. They're all going to have the same exact. All going to have the same exact amount of particles, but they're going to have different masses, and the masses itself are going to be the same. So I might have just confused you there, because I did just mess up a bit. So pretty much what I mean by saying that is that let's say we have something like lead, for example. So what is lead's atomic mass? Well, lead's atomic mass, so let's just give this equals to 207 U. And I'm just going to represent this atomic mass by representing it with the letter U. So lead is 207 U. Well, its molar mass is going to be 207 G/mole. Its formula mass is going to be 207 AMU. And its relative atomic mass, is going to have just 207, no units. I want to point out that all of these numbers have the same exact mass. It's not that molar mass is automatically created 100 pounds more than the formula mass. That's not how chemistry works. You cannot create matter. And that's one of the very basic concept of chemistry, which you've learned in previous courses. You cannot create matter. Matter cannot be created out of the values. That's why we have laws such as the law of conservation of mass. That's why when you're going from molar mass formula and relative, you're going to represent it with different units at the end. But the main concept is that the mass itself is going to stay the exact same. You're not going to have a different mass in molar and a different mass in formula. It's going to be the exact same. Just the way you represent it by using different units is going to make the difference. So let's say we have something like this. Let's say we have lead again, and lead is 207U. And carbon 12 is going to have 12.U. Well, what it's saying is that both of these have 1 mole. 1 mole. But that mole is simply just representing its particles. 1 mole of lead, 1 mole of lead, is going to equal 207 G/mol. And 1 mole of carbon is going to have 12 grams. If you see, the molar mass is different, but if you remember, the amount of particles itself are the same. That's going to be the 6.022, 6.022 times 10 to the 23. The amount of particles are the same, but the actual molar mass is different. So if we have, let's give an example then. So let's get rid of all of this. And let's say we want to do an example. Well, let's give the example of this. So we have H3O2. H3O2. Well, let's figure out its molecular mass. So molecular mass. And then let's do a molar. And then let's do a relative. I'm going to work from top to bottom, or bottom to top, I mean. Well, let's do its relative first. Well, we know that hydrogen is going to have more or less about a 1, so as its weight. So we have 1 times 3, well, that's going to be 3. We have O2, so that's a diatomic right there. Well, it's going to be 16 times 2, so that's 32. So then we have 32 plus 3. Well, all that's going to be is simply just 35. 35, no units. Move on to molar. Well, we know that matter cannot be created, so we're just going to write 35 G/mol. The molecular, all we're going to do is that we're going to write 35 AMU. You can write molecular, you can write formula, it just depends on the type of bond. We should actually write write formula because of its bond itself. It's not a molecular bond, it's actually an ionic. So we're going to formula. Formula. Now some people get confused when they hear the words formula and molecular and stuff like that. It's fine. If you rewatch this video after the first initial watch, you'll understand the different concepts of it. And that's why I always recommend watching my videos twice, because the first time it might sound a bit hazy because it's still a new topic. The second time you'll properly understand it. So let's look at actually calculations, because that's what a lot of people mess up on. So let's say we have a calculation where we have carbon dioxide. Actually, let's not do carbon dioxide. Let's just do the same thing. Let's say we have H3O2. H3O2. And now we're going to be doing mole calculations, actually. So pretty much what we're going to have is that we're going to have the amount of mole. So we have H3O2, and then it's going to be inside a sample of 2 grams. So what we're going to have is we're going to have 2, or not 2 grams, just we're going to have it 2 times 10 to the 23. 2 times 10 to the 23. And you want to find the amount in mole. So what we're going to have is that we're going to have N, and then we're going to have H3O2, H3O2. And we're going to represent this by using the actual amount. So we have 2 times 10 to the 23 over Avogadro's constant. So I'm just going to represent Avogadro's constant by using this. So we have AC. Let's do that. And then that's going to be MOL to the negative 1. To the negative 1. Now, if you actually do this calculation, I'm going to let you guys do it by yourself, and I'm going to guys give you 20 or 10 seconds to actually do it. So, I'll give you guys 20 seconds right now. Okay, you guys should have gotten it by now. So if you did the calculation on your calculator, what you should have gotten is that you should have gotten 0.33. So what this is going to represent is that we have 0.332 MOL. Now you're going to be extremely confused, and I did this on purpose. I did not tell you how to calculate first. I just did a calculation so that you're extremely confused right now. I'll tell you why. If we get rid of this, I'm going to explain why I did it the way I did. So, what the question was, is that it asked for calculate in mole. Let's just get rid of that. Of H3O2. H3O2. So that's going to represent the NH3O2. And a sample of 2 times 10 to the 23. That was the question itself. And when we're doing these questions, what we're first going to do is that we're going to have the number of particles on top. So this number of particles, which is 2 times 10 to the 23, that's going to be at top. So we have 2 times 10 to the 23. Number 1, we got that good part. Good. Over that, what we're going to have is Avogadro's constant, or mole. So we're going to have the 6.022 times 10 to the 23 mole negative 1. And what you're pretty much doing is that you're simply just doing it Avogadro's constant over L, which is going to be your number, and then we have Avogadro's constant, and we're just going to be pretty much just dividing it. We're just dividing one number by another using the same way. And the relationship between the amount and the mole of the number of particles in the sample is pretty much this number. The 2 times 23 is what we're actually doing for the mass of the sample. And when we're doing this n, all we're representing with this n is that what we're actually doing the reaction of. So if we did a reaction like this, for example, I'm going to give you another reaction, and this time I'm going to not tell you again, but I want to see if you guys are able to figure it out by yourself. So let's say we have, let's say we have this, okay. Let's say number of hydrogen atoms. Number of hydrogen atoms in 1.5. Actually, let's just do it 2 again. and 2 molars of H3O2. H3O2. And I'm going to give you guys 1 entire minute to solve this question by yourself. After 1 entire minute, I'm going to actually tell you guys the answer itself. Okay, I'm actually going to make it a bit shorter than 1 minute because I feel like this is going to be extremely prolonged if I keep giving very long breaks. So what we're doing inside of this is that we have to look at the number of hydrogen atoms in 2 molar. Well, 1 mole is going to consist of 3 atoms of hydrogen, so 3H. 2 mole equals 6H, because we're doubling it. So pretty much what we're going to do now is we're doing the number of atoms equals to the number amount in mole n times the constant. So this one, the only thing we're going to do is that we're going to have 6H, 6 MOL multiplied by the constant itself. So you have 6.02 times 10 to the 23. 23 negative 1, and then mole negative 1. And that's pretty much all you guys are going to have to do. So I'll give you guys another time to do the calculation again. Okay, so what you guys should have gotten is that we have 3.6 multiplied by 10 to the 24 hydrogen atoms. And pretty much and that's all that it's actually doing, because you have to calculate it inside of the molar itself. We could have just said 6 hydrogen, but that would have been wrong. Because what we're doing is that we also have to look at the amount of that 6 hydrogen inside of the actual 2 molar. So that's why we did what we did. Leaving off this video, I hope you guys have understood why we did what we did in each of the calculations, what Avogadro's constant is, the difference between the relative atomic mass, molecular mass, molar mass, and different parts of that. So leaving off with that, Professor Anwar out.